do we do as network geeks if we have to deal with counterfeit products, be it because a nation state is pushing to embed stuff in the chips, or because of some other reasons, maybe somebody's trying to sell chips cheaper and make more money, and this causes the chips to be less reliable. So the research that we're going to share here is particularly on that topic. How can we quickly determine if a chip is counterfeit? I also want to acknowledge Dr. Chad Lau there as well. And also Sean, he's actually a sophomore, but do not be misled by that. He's extremely bright, and he has put a lot of effort into this project. He actually did a lot of the measurements. So without further ado, Sean.
Hi everyone, thank you for that introduction. My name is Sean Klein. I'm a sophomore at Purdue studying electrical engineering. Grateful to be here representing Dr. Peter Bermel, Kevin Yu, Weilun Cheng, myself, Dr. Chad Laux, and Dr. Krasimir Tsvetanov, as well as our sponsors from Los Alamos. That is Dr. Travis Klein and Dr. Boris Gelfand. I'm very excited to present the research we worked on the last semester and that we plan to continue working on after this conference. So Krasimir covered a lot of these, the rationale and goals, so I'll start off with kind of what are the objective of my contribution and some of us on the Purdue side were trying to do, which was to build a classification framework. So traditional classification methods are often destructive. So if you're taking apart a chip, you're not going to be able to reuse it in future studies. So we want to make sure that if we're testing a chip, it's non-destructive, and therefore we can continue to use it if in case it's authentic, right? So we explored multi-instrument analysis from instruments such as like spectrophotometry and profilometry, and then we fed statistical modeling and multivariate analysis to distinguish an authentic from counterfeit sample. And then our goal was to develop the reproducible, scalable framework that you guys can implement into your supply chains, etc. So I want to point out the image at the bottom. I'm going to go into that in a little bit, but that's kind of the basis for our research. So we had 5 different vendors, one of them being a known authentic, and I'll discuss that here. So we chose Raspberry Pi microcontrollers, highly available, and they're both accessible from reputable suppliers as well as unreputable suppliers. And we selected across different locations. We tried to develop a baseline based off of our known authentic, which was DigiKey. And we know DigiKey is authentic because they're a verified Raspberry Pi wholesaler. And then we tried to use the vendor source material, so exactly from Raspberry Pi, their specifications to identify sort of what are we looking for and then what would be suggestive of a counterfeit. And then going a little bit more into the sampling strategy, so we had the reference batch, so we had about 20 authentic and then 20 samples from each other vendor, and they were from AliExpress, and we tried to have them represent supply chains that are across the world, so representative of what you might get if you were to buy from AliExpress or have exposure to these various supply chains. So going into how we did the analysis, so we had 3 kind of categories. So we had mass measurements, which covered the analytical balance, and then visual and structural analysis using white light microscopy, UVA fluorescence microscopy, X-ray microscopy, laser profilometry, UV, vis, and IR spectroscopy, and then X-ray microscopy. And then elemental and chemical analysis, which included X-ray fluorescence, X-ray photoelectron spectroscopy, and laser-induced breakdown spectroscopy. So all of these, like I highlighted before, are non-destructive, so they're not going to destroy your chips or prevent you from using them after doing this testing. So moving on to the first instrument, so white light microscopy, you can kind of think of that as like a microscope. So we shined white light onto the surface of the sample, and we took pictures of it. It's not too complicated, it's not too complex, and our output was that, we had these high definition images, and we took about 2 pictures per sample. And you can see that here. So, what's interesting about this is just off of a baseline like visual characterization, there's a clear difference. So on vendor 1, which is our known good, authentic, from DigiKey, this is a sample. You could see the surface pattern of bonding wires on the back surface. The notch shape is clearly circular, and the thermal vias are in a 4x4 arrangement. While on the right-hand side, you see vendor 5, it was an AliExpress vendor, and the notch shape is more oval-like, very different than our previous circle-like. And then it's kind of look like it's sanding. So we think that maybe the back was sanded, and then redone, or it was a different chip that they used actually and just repackaged as a Raspberry Pi chip. And then like really one of the most definitive characteristics are the thermal vias. And although like we can't say for sure, I mean Raspberry Pi's manufacturer specifications don't have a 5x5 thermal via array on the bottom. So that's kind of definitive, or could be definitive. And then moving on to UVA fluorescence. So we were trying to evaluate the viability of this method. Very similarly to white light microscopy, it's relatively simple, but theoretically, we saw the results from white light. It could have very pronounced differences. So hopefully we were looking for differences in ink reflectance, and differences in the fluorescent spots can serve as those counterfeit markers. And then as the measurement info, we had an output of high definition images similar to the previous instrument with 3 measurements per sample for a total of 300 measurements total. And you can see here we had various places on the chip that we measured, and those are relatively arbitrary. We felt that those were going to be strong places to profile, and showing you the results here. So not the results yet, just going more into the methodology, apologies. We built a O-ring with the light strip inside to maximize the surface. We also built a little bit of software to handle the images and manage the data. And then here's now the results. So basically you can see on the bottom here, we identified some places on the surface of the chip where there might be some fluorescence indicators. You can see those highlighted in red circles. And then you can see on vendor 5 specifically, there might be a different font, and it's a little bit darker than the other vendors. And our goal from this instrument was to establish an RGB baseline from the authentic sample under the UVA light, and then to use maybe classification algorithms, neural nets, to sort of quantify the difference. Moving on to X-ray microscope. So XRM is a powerful imaging technique that uses X-rays to non-destructively and non-invasively look at the innards, insides of the chip. So we were trying to have a comparison side by side between the authentic vendor versus the potential counterfeits. And our data that was outputted was a 3D image. And we have one measurement so far because the instrument takes about 5 hours. And it's a fairly substantial process. You can see the picture of it over here. And here's the result just from that one measurement. So we could see that, you know, this is an example from vendor 1, so it's a known authentic. And we compare the bonding pads and bonding wires to this manufacturer specification, confirmed that it's an authentic, at least by this instrument. And hopefully we would apply this measurement tool to other chips and see if there's any differences. It's actually known in literature that sometimes if they're repackaging other chips and trying to resell them, that there might be differences in the bonding wires and bonding pads. So moving on to our next instrument, XRF. So XRF uses X-rays to determine the elemental composition, and it's kind of focusing on the bulk materials and those that are greater than or equal to period 3, so they're heavier elements. And the X-rays from this instrument will penetrate the entire chip. It's not going to be as discriminatory as the following method you'll see, but it's able to give us a general overview of what elements are present and what elements are not present. And our measurement info was that we got elemental composition in the form of weight percentage relative to the entire chip. And then we got 1 measurement per sample for a total of 100 measurements. And you can kind of see the results here. And so what I want to point or highlight is that like phosphorus, for example, is only present on vendor 5. Now, we're not 100% sure why that might be the case, but literature and previous research would suggest that maybe there was black topping involved, so they repainted the surface potentially with a material that had phosphorus in it. Or I want to point out that bismuth is only present on vendor 4. And, you know, of course, silicon is going to be present on all of the vendors. I mean, the chip is made of silicon, but we can maybe use these elements that are different as discriminatory for future analysis. And then moving on to this slide, where we just see across the board these elements are present. It's not particularly like astounding that iron would be present on the surface of a chip or inside a chip, but you know, it just tells us that this is not where we need to be looking for future analysis. Moving on to the X-ray photoelectron spectrometer, or XPS, and we use this to study the surface chemistry of materials by determining the elemental composition. And this tells us that this tells us the elemental composition of points on the surface, and at a very precise depth of 2 nanometers. And this is for lighter elements greater than or less than or equal to period 3. And the binding energy of the electrons that are outputted off the surface will tell us the elemental makeup and chemical states. And we got 5 measurements per sample for 25 total. That final bullet point is a little off. And you can see the points that we measured here. So we had 2 inside the logo and then 2 on the outside of the logo. And that was just because we thought that if there was any repainting done on the surface, that maybe they didn't touch the outer parts and maybe they only touched the logo. So our hypothesis testing was to use Mann-Whitney U. So because of the low sample size and the equal variance that we evaluated, we decided that a ranked order test would be valuable. And that tells us whether one group's distribution tends to have higher or lower values than the other. And it doesn't assume normality, which this samples did not have. So I want to highlight on here that we found significant differences between points 1 and 2 relative to the vendor 1 across the board for all of the elements. And here you can see we're displaying the U value, P value, rank by serial coefficient, and common language effect size. We saw a significant difference in carbon for all vendors and a high rank by serial coefficient, which provides some justification for our results. Moving on to points 3 and 4, which was just comparing the outer points between the other vendors and vendor 1. We again saw some significant differences, and that was primarily between vendors 4 and 5, and our IRBC was relatively high, which justified some of those results. And moving on to the Lambda 950 spectroscopy, and this uses visible light on the surface of the chip and sees what's transmitted off the surface. So we had mentioned that we used fluorescence microscopy. This is kind of an extension of that, but it's over a greater wavelength. So you're talking 200 to 600 nanometers as opposed to more constrained. And that way we can get very specific about what nanometer wavelengths are present on the chip and what might be signifying counterfeit or not. So as a measurement info, we took 5 measurements per sample for a total of 500 measurements. And here is just like an overview. This is not too statistically, it's not very in-depth statistical analysis, but you could clearly see that there's a difference in mean reflectance compared to vendor 1 across vendor 5, or across all 5 vendors. And this is over the 400 to 600 nanometer wavelength. And this is visible light. So you could see, I mean, it's very visual that very clear that there's a visual difference. And vendor 2 is consistently higher, while vendor 5 is consistently lower, and you'll see more of that in the next slide. So I again want to highlight that we used hypothesis testing on these samples. We used specifically the Mann-Whitney U to compare the distributions, and we did not meet normality assumptions, which is why we utilized this, and we had equal variance to justify. So I want to point out here, this is the mean reflectance. So you can see that vendor 5 is, like you'd seen previously, consistently above, while vendor 2 is consistently below. And we did see significant results on vendor 2 and vendor 5, that's why I highlighted those previously, which suggests that they were, across this wavelength, they were significantly different. And the vendor 5 rank by serial coefficient for the difference is higher than vendor 2, suggests that vendor 5 is more justifiable via the analysis we did. Moving on to LIBS, which is laser-induced breakdown spectroscopy. And this takes a laser and it basically ablates the surface of the chip, and then we analyze the plasma from it. And it's on the surface 2 to 10 microns deep. And the output of the instrument is a weight percentage, very similar to previous instruments. And we took 16 measurements per sample for a total of 1,600 measurements. And here you could see the output, and this shows the LIBS spectral output, where the peaks correspond to specific elements, and large peaks shown here are for oxygen and silicon. We haven't had time yet to go through the analysis, but effectively we got the results, and we can see here as an example of such. So going through how we're going to use the results in the future. So we plan to use the weight percentage for validation of our previous instruments, because elemental characterization can be finicky sometimes. I mean, if you have a fingerprint on there, that could affect the composition you're reading. So we're going to use the validation across the instruments. And so X-ray fluorescence, for example, and XPS can be validated by this method. And we found that we can likely compare silicon concentrations between the different samples. So now going into the most straightforward and probably easiest to understand, the analytical balance. And although it might be deceiving, this is actually pretty effective at seeing differences between the chips. And we chose it because of its low complexity and how fast it was. And we outputted a continuous mass value in grams with 5 measurements per sample for a total of 500 measurements. And you can see here, I know this is a lot on the screen, but I just want to highlight that we had a very high statistical power for saying that the vendors 2 and vendors 3 are statistically significant, and our Cohen's d was very high for this. So I'm not sure how many of you are familiar with statistics, but we were very confident that these results are pertinent to what our analysis was, and we felt very strongly about them. Going into laser profilometry, it's a non-contact optical measurement that analyzes the surface topography of the given sample, and it's supposed to bring up the texture difference up to 0.1 nanometer accuracy. And then for info for the measurements, we got 5 features per chip and 6 different positions on the front-facing surface that we analyzed, and for a total of 600 measurements. We can see here some of the outputs. So we haven't done a full statistical analysis of this measurement data, but we could see that there is some variance there's different levels of variance across the different surface features. And I'll go into more so why that is the next slide. But as an overview of the feature, SA is the mean absolute height. The SC is the maximum peak to valley height. The STR is a 0:1 texture aspect ratio. SPC is the mean curvature, and SDR is the developed interfacial ratio. And then we can see here a box plot of the mean across each of these different features, not including the dot because we saw a lot of variance specifically in that dot region. And we think that a potential cause of outliers that you can see here are surface sanding or polishing, re-etching or laser ablation, coating or repainting, or foreign material deposits, all of which you would see on a counterfeit chip. And going a little bit further into actually validating what we've seen. So we used PCA to reduce the dimensionality because we have 5 features we can't really compare unless we use a hot tailing Steer Manova, which you see here. Rather, we tried to use PCA as a preliminary analysis to see if we could group the vendors. And it's very clear that vendor 5 over here has a distinct grouping when applying this algorithm. And this algorithm is very well known in literature. It's not particularly unique. And it suggests that if we can do this on just like using a simple, straightforward algorithm like PCA, then if we use more complex machine learning models, we can further isolate and cluster these groups. So I want to go into how we're going to combine all of this to build a framework. So we want to utilize Bayesian optimization to develop a ranked list of instruments that what's going to provide the most value. So obviously we know that our friends in industry don't have access to $500,000 machines, and they don't have access to the total birth of knowledge you need to utilize these methods. So we want to try to identify what are the quickest, the easiest, most accurate and portable and complementary instruments to each other, so that if you guys wanted to implement this in your supply chains, you can. And so we have 2 phases, with phase 1 being a focus on accuracy and time, and then phase 2 being incorporating portability and complementarity. And I just want to highlight something about the accuracy. So when we say accuracy, we're talking about if we were to build a model on this, how well does it classify? So for example, you saw PCA as an example of a machine learning model. If we are to build a model per instrument, how well is it going to group these different vendors? And then we're going to evaluate the accuracy of the said models on key metrics. These are pretty standard for machine learning models, and then go from there. So we're going to try a bunch of different methods to cluster the data and then see what the output is. And then we have identified 3 possible approaches. So upper confidence bound, or UCB, it's going to use an optimism bonus to balance both uncertainty and accuracy. So if you're not familiar with Bayesian statistics, it's effectively telling you what's the probability given A of B. So we want to understand, okay, well, you have all of these different factors that are contributing to this uncertainty. What's the most likely, and how do we build out a ordered list of it? And you can use Thompson sampling and then tree-based Bayesian statistics as well. This is a novel application of this statistics, so we're hoping that we can apply it to this research and have an output that's usable by industry. And I want to go into the formula we're going to utilize for that purpose. So for phase 1, I mentioned that we want to highlight time and accuracy. So accuracy is going to be a fixed number. So 0.66, like if you're classifying 66% of your samples in the right cluster, your accuracy is going to be higher. And then we also have a time for the length. And then the lambda is the trade-off. So how much time are you willing to sacrifice for accuracy and vice versa? And a high lambda would prioritize the speed, while a low lambda would prioritize the accuracy. And then we're going to run the full optimization process on a few different lambda values. But what we ideally would like to have is, if you guys feel that time is more important than accuracy, or accuracy is more important than time, you'll be able to build your own methods based off of our results. So it's going to be very interchangeable to your needs. So going into a summary overall of the findings. So we did have statistically significant differences between vendors across multiple instruments. And this is the first time implementation of spectrophotometry, XPS, UV fluorescence, LIBS, and gas chromatography, and laser profilometry for counterfeit detection. And we know that that's a long list, but you can think about it like we're using different methods. So surface analysis and chemical analysis and elemental analysis. This is the first time some of these instruments were applied for this purpose. And then we were able to process and quantify the raw data. We cross-validated across the instruments, so we wanted to make sure that there was a consistent reading across some of our results. And then we explored we're exploring currently potential integration with ML models for the instrument down selection to optimize those metrics, like I mentioned before, accuracy and time. And in the future, we're planning to use gas chromatography. And to explain gas chromatography simply, it's basically analyzing the volatile organic compounds that come off a chip. So if you ever walk into a room that has cleaning products, you're smelling the volatile organic compounds. And so we think that if we analyze those compounds, we can identify what chips might be counterfeit, which ones are not. We're working off of previous Purdue research. And then we're still going to continue our quantitative analysis, expand the UV fluorescence work, and then applying our methodology to other chips. So we're looking at maybe using PCB boards or other chipsets to validate some of these methods, because if we're seeing consistency, then that could suggest that these are pretty realistic to supply chains in general. And any questions? Thank you for listening to my presentation.
Hi, excuse me, my name is Lee Howard. I have no affiliation. I have two questions. I think they're almost exactly the same. So right now you've basically taken one chip, by the way, fascinating work, really interesting. Thank you very much for bringing it here.
Of course.
So you took one chip from each of 5 different vendors. Do you think that if you were to get 5 or 20 chips from each of those vendors, that there might be more variation? Like if you've got, like vendor 1 was the known good, but might there be more variation, especially between manufacturing lots or batches? Like if you took one from last year, one from this year, same chip, but different manufacturing times and places, would there be more variation there that would question not question the validity, because there's enough here that you're clearly finding data models, but is there more research required to just test more samples?
So sorry, I didn't clarify that point. So we did a total of 100 samples. So there were 20 chips per vendor.
My bad, thank you.
So the statistical analysis was of 20 chips. Theoretically, we could do more. That would be more representative of your population.
I'm happy, thank you. That was the great answer. Maybe I just missed that at the beginning. My second question is, I think it's the same, it will turn out to be more or less the same, the actual measurements for different chip manufacturers. Like, so you're using a Raspberry Pi, but if you were to go use, a laptop CPU or a chip from a phone, I assume you'd have different measurements, but the same kind of variance between different vendors.
That's the hope, yeah.
Can't wait to see that borne out too. Great work, love it.
Thank you. Thank you.
Before the next question, I was just going to add that actually we're looking at turning this onto commercial equipment, communications equipment, and we're looking for partners in that. As you can see, we have the capability to do it. We're a university. Many corporations just cannot justify the ROI on hiring the specialists to do this type of work and procuring this equipment, but we can very easily do that in academia, and that's what we do, right? And this is why I personally am kind of staying between industry and still teach part-time at Purdue, because I think there's a lot of value in merging the resources of academia and industry.
Sure. Hi, Tim Novacek, also unaffiliated. It sounded like vendor 5 you were pretty confident was not legitimate.
Yeah.
In the end, what confidence do you have in how many of the vendors were selling legitimate products versus illegitimate products?
So we saw pretty consistent differences between vendor 2 and 5 and vendor 1. So it's kind of hard to say if the inconsistency is due to them purposely counterfeiting their chips or because they had different manufacturing. So it's either they took another product, repainted it, sold it off as Raspberry Pi, or they had a different manufacturing process that maybe saved costs, and then it's still kind of Raspberry Pi, it works the same way. So we're unsure of the complete understanding of like, okay, is this a counterfeit or is this like purposely counterfeited for nefarious purposes, or is it because like they just try to cut coders? We're not sure yet, but we definitely know that there was vendor 2 and vendor 5 were very different across the board. Thank you.
Yeah, and if you're curious why we're looking at the physical packaging, so we're assuming that this is a chip that's functionally working. It's in some kind of equipment, and then we want to test, hey, this thing was shipped. Is this router actually really containing original parts that are also tested, temperature tested, all kinds of regression testing that has been done on them, and then shipped? Or is that some kind of an equipment that was done in a garage somewhere, in a small country and then shipped as a counterfeit? Or is that actually a device where a particular nation state embedded a particular chip in that device, either because they want the chip to fail after a certain amount of hours? Let's say, think about a repeater in an undersea cable, right? Once this thing burns, you have a bit of a problem replacing it. It's expensive, right? So those are the threat vectors we're looking with this particular research. We're also looking at other research where we'll be doing full regression testing of chips, but currently this is the scope of the research. Any other questions? All right. As I mentioned, we'll be looking for partners as well. Also, the slides will be published. I know there was a lot of information in those slides, so we'll publish those. And there's future work that we're looking at other chips right now, and there's more stuff we'll be looking at. So, thanks everyone.